called Less is More, code-based signatures without syndromes. And they gave a new signature scheme based on the hardness of the permutation equivalence problem or the linear equivalence problem. But in this very short talk, I'm just going to talk about the permutation equivalence problem. What is this? In this problem, you're given two linear codes, C1 and C2, and a promise that there exists a permutation that maps one to the other. And the problem is then to find this permutation. So you find a permutation pi, so that pi of C1 is equal to C2. And by pi of C1, I just mean the code that you get by applying the permutation pi to every code word in C1. And this gives very nice key sizes and signature sizes compared to other code-based signature schemes. So this is very promising, but of course the question is if it's secure, because if it's too good to be true, then it's a good target for cryptanalysis. So that was the goal of my work, to try to break some of the parameter sets that they proposed. And we're going to start by looking at one of the existing algorithms to solve the permutation equivalence problem. And this has two steps. The first step is to compute all the minimal weight code words in our two codes. And this is the expensive step. And the second step is, once you have those two sets, then to recover the permutation itself. So I'm going to give a little example. So suppose that these are the minimal code words in C1 and C2. Then if you look at the first position in C1, all the code words have a 1 there. And this is also the case for position 10 in C2. So you know that the permutation has to send the first position in C1 to the 10th position in C2. And then if you look at the 5th position in C1, there you got 2 1s and a 0. So you know it has to be mapped to the last position in C2. So this is very roughly the ID. And you can proceed in this way and hopefully recover the entire permutation. And now we're going to go look at the new algorithm, which is a bit similar, but instead of matching the positions in C1 with the positions in C2, we're first going to match the code words, the minimal code words in C1 with the code words in C2. And if you look at the first code word on the left, it has 1, 4, 1, 2, 2 3s, and a 5. So you know that its permutation needs to have the same set of entries. So you immediately know that it has to correspond to the second code word in C2, right? And this is because the set of entries is unique, so it only can correspond to one of the minimal code words in C2. And you can do the same thing for the other code words. And once you know which code word in C1 corresponds to which code word in C2, it's really easy to get information about the permutation, because you know, like the 4 has to be mapped to the 4 on the right. So the second position needs to be mapped to the third, and the same for all the other unique entries. So this is really easy. But why is this more efficient than Leon's algorithm? Well, it's because we don't have to compute all the minimal code words anymore. Because as soon as you've got one minimal code word in C1 and a minimal code word in C2 with the same set of entries, then you don't need to know the other code words. You can just assume, okay, this one is a permutation of the other one, and then you got information about your permutation. And in fact, you don't even have to compute minimal code words anymore. You can compute code words at a higher Hamming weight, and this will still work. So yeah, here's a graph that shows the complexity of the new algorithm in blue versus the existing one in yellow. And you see that for increasing field size, which is the x-axis, the gap between the two algorithms grows. And in practice, the algorithm works very well, because for the parameter set that the less designers proposed, we can break the problem in only 2 seconds on my laptop. So I'm not going to talk about the linear equivalence problem in this talk, but we did propose some new parameters that resist our attacks. And if you use those, then the size of the signatures increases by roughly a factor of 3, and the size of the public keys increases by roughly a factor of 22. So this is quite painful, but if you compare to the existing code-based signature schemes, then it's not so bad, because it still compares relatively well. So that's all I prepared. Thank you for listening.
Thank you very much. I think you can unshare your screen for the next speaker, and we'll collect questions for the channel and get back to you later. Our second talk is, so I believe the speaker would be Chelsea Comlo, but I'm not sure because it doesn't say. And the title is Frost Flexible Round Optimized Schnorr Threshold Signatures.
Nope, that's me. Okay, you can see my screen, right?
Yes, we're good.
Okay, great. All right, so today I'm going to be talking about FROST, and that stands for Flexible Round Optimized Schnorr Threshold Signatures. And this is joint work with Ian Goldberg and joint work between CRISP at the University of Waterloo and the Zcash Foundation. So just as a quick recap, what are threshold signatures? So they're very similar to single party signature schemes in that there's one public key that represents all signers and used to verify messages. However, the private key is secret shared among a set of parties. So here we show a 2 out of 3 scheme where you need 2 signers in order to issue a valid signature, but there are 3 possible signers. And most importantly, in threshold signature schemes, the full secret is never reconstructed. So participants perform signing using only their secret share. So what are the high-level contributions of FROST? So first, we present a 2-round threshold signing protocol, or it can be optimized to a single round protocol with a pre-processing step. Signing operations are secure even when they're performed in a concurrent setting, meaning that many signing operations can be performed at once. And this improves upon prior schemes in the literature. Signing can be performed with a threshold number of signers, T, where T can be less than or equal to the number of possible signers, N. So as we saw before, you can have a subset of signers, not all signers need to participate. And finally, FROST is secure against an adversary that controls up to T-1 signers. So I'll just walk through the protocol at a high level. So first, for keygen, this can be performed either via a trusted dealer or via a distributed key generation protocol. So trusted dealer is where one signer or one participant generates all the keys and distributes it to all participants. Or DKG, no participant is trusted more than any other. But what's important is that after keygen, every participant will hold this secret share SI, and they'll also have a public key YI, but we only use that internally for verification during signing. But as we saw before, there's a joint public key Y, which represents all signers. So for signing operations in FROST, we'll show this using a signature aggregator, and this is kind of a centralized role that's used for coordination, but it can be performed without centralized roles and in 2 rounds. So I'll show this using the pre-processing step, but this can be performed in 2 rounds if desired. So the first step for FROST signing is this pre-process step. So every participant will start by generating a tuple of 2 nonces, and then they'll generate 2 commitments to those nonces. They'll store these values locally, and then they'll publish their commitments somewhere. Here we show this as a commitment server, but again, this can be just the first round in the signing protocol where they would send these commitments to all of their participants. And then for the signing step, we show this using a signature aggregator, but this can be any signer, where essentially they just choose all of the signers that will be participating in the signing operation. So they start by choosing the commitments that all of these signers will use, and this is represented by B. And then they send the message to be signed M and B to every signer. So every signer starts by generating what we call a binding value. And this is the hash of the message, its B value, and the participant's index. And then they generate the group's commitment. And this is essentially just a combination of all signers' commitments along with this binding value. Then they generate the challenge. This is identical to in single party Schnorr. And then the response. And here we can see that knowledge of these 2 nonces is required, or you need to have knowledge of these 2 nonces in order to essentially invert and remove this binding function. So this is really important to the security of FROST. Then all the signers return their responses. And then the signature here is just a sum of all of the signers' responses and then the group commitment. And what's important is that this is actually identical to single party Schnorr. So what are the overall takeaways from Frost? One, we improve upon prior threshold signature schemes because we define a single round threshold signing protocol with preprocessing, or a 2-round scheme that is secure even when signing is performed in a concurrent setting. And one thing we kind of want to emphasize is that the simplicity and flexibility of Frost makes it attractive to real-world applications. I think I accidentally have this point twice, but one thing that we're excited about is that Frost is actually under consideration right now by the CFRG, and we're going to be presenting Frost at an upcoming NEST workshop. So thank you very much, and that's my talk.
Thank you very much. Our next talk is Boolean ring cryptographic equation solving. May the speaker come forward.
Hello, I'm Sean Murphy.
Thank you.
Can you see me? There was a problem with my video. I look very weird.
Oh, no, you look perfect.
Okay.
Can you share your screen?
Of course. Okay, so this is work with Mara Patterson from Birkbeck in London and Christine Swart in Cape Town. So we're considering the problem of solving a polynomial system f1 equals f2 up to fm equals 0. We're going to look at it over GF2, but first to give some background on the general approach people use to do this over a finite field. The basic idea is they generate further polynomials up to a given degree. So we generate lots of polynomials, and then we use a form of Gaussian elimination to find a univariate polynomial or a bivariate polynomial in the span of these generated polynomials. We can factorize this univariate or bivariate polynomial. This gives us a linear factor, and potentially we can substitute one of the variables to get a smaller system. For equation systems over GF2, generally these field equations xi squared plus xi equals 0 are added to the original system. These essentially force the solution to lie in GF2. So one problem with this type of approach is it's very specific on the variables. If we make a linear change of variables, we can get a very different performance of the algorithm. So if the equations essentially add up with the coordinate axes, then the efficiency can change greatly. So we looked at an approach where we mapped everything down to a quotient ring. Essentially, you can see the ideal of this quotient ring is these field equations. And the idea is we generate the extended systems before we generate higher degree polynomials, but then we map them down to this Boolean ring. So we just have Boolean elements, all satisfying z squared equals z in this Boolean ring. We then showed that all we have to then really worry about is the elements, these Boolean polynomials that are quadratic. So we look at, we find the subspace of quadratic elements. This is obviously a very simple thing to do with linear algebra. And then we find these matrices, which we call partial matrices. So if you look at the definition in the blue box, we write out a quadratic element, and then we extract the coefficients of the quadratic terms, the aij's, and we just write them in a symmetric matrix. So you can think of the ijth entry giving the partial derivative of this function with respect to j and giving the coefficient of zi. Okay, so we're going to look at what one of these quadratic elements looks like if it's this partial matrix has rank 2. So there's one with 6 variables, a quadratic element, partial matrix there of rank 2. And it turns out you can extract the rows from this matrix. It has rank 2, so it can only have 3 non-zero rows, rank 2 over GF2. And if you do this construction, you take G plus the first one is the linear polynomial is essentially given by the first 2 rows of this matrix, and we get a linear function out of that. And it turns out, for reasons we explain in the paper, that this linear function that we get by doing this takes a value 0 for 3/4 of the 0 points of G. So in some sense, this linear function lines up with G with probability 3/4. And the point about this is we can generate lots of these linear terms, which take the value 0 of the solution with probability 3/4. So this gives us a method. We find the quadratic subspace of the Boolean image of the extended polynomial system. We construct these matrices, and then we look for matrices of rank 2, which we can do by something called the kernel method, essentially just linear algebra. And having constructed this matrix of rank 2, we can extract the rows, and this gives us linear expressions L, L dashed, L double dash 3 for each construction we make, each taking the value 0 with probability 3/4. So we now got a series of linear equations that hold with probability 3/4. This is called the learning parity with noise, or LPM problem. There are algorithms that solve it sometimes relatively efficiently, such as the BKW algorithm. So in general, we might expect this approach to be more efficient than comparable methods like extended linearization, XL, because our approach is geometrically invariant, whereas the other methods are not. The degree required by this approach should essentially be the same as the degree required by XL-like methods, so we have to do the same kind of multiplication. And in fact, we found an example in the paper where we could actually do it faster, a lower degree than XL, so considerably faster. The system, this approach should be much more straightforward, as the first thing we do is we go down to a much smaller quadratic system, so simpler polynomials to handle. And this approach potentially just gives a direct solution, whereas the XL approach gives a factorization and a number of possible solutions, which we then have to try in turn. And it also establishes a connection between solving multivariate polynomial system over GF2 and an instance of the learning parity with noise problem. Okay, so that's the whistle-stop tour of the paper. Thank you.
Thank you very much. Can you unshare your screen for the next speaker?
Yes.
Thank you. Our next speaker is Peter Kudas, and he will present the paper Trapdoor DDH Groups from Bearings and Isogenies.
Okay, can you see my screen?
Yes, it's perfect. Go ahead.
Okay, so I'm going to talk about joint work with Christophe Petit and Javier Silva about Trapdoor DDH groups from pairings and isogenies. So let me briefly recall the Diffie-Hellman problems. So let G be a cyclic group and with generator P. And the computational Diffie-Hellman problem, CDH, is when one is given P, A times P, B times P, and one has to compute AB times P. And the decisional version of the same problem is when one is given P, A times P, B times P, C times P, and one has to decide whether C is AB or C was chosen at random. And one has to be able to distinguish that with a probability significantly larger than 1/2. So this problem is assumed to be hard for some groups, and it has many applications in various crypto schemes. However, there is a well-known instance when solving DDH is actually really easy. So when one has access to a bilinear pairing on the group, which is non-degenerate on that cyclic subgroup, then one can actually solve DDH easily by computing the pairing on APBP and comparing it with ECPP. And if they're equal, then that's a DDH tuple. And if not, then it's not. However, the pairing doesn't seem to help in solving the computational version of the problem. This motivates a definition of a primitive called Trapdoor DDH, where with some Trapdoor information, one distinguished party can solve DDH instances efficiently, while without the Trapdoor information, DDH is still supposed to be hard. And the computational version is supposed to be hard even with the Trapdoor information. So this primitive was first constructed by Dent and Galbraith in 2006. And then there were several other constructions by Seurin. And they both had various constructions and different applications, but none of the applications were really compelling. And then Seurin identified some problems with existing Trapdoor DDH constructions and posed the open problem that if those constraints are satisfied, then maybe much nicer applications are possible. And those two are, so one would need a group of prime and public order, and the other one is the ability to be able to hash into the group efficiently. So our main goal was to solve Ceran's open problems and come up with a new trapdoor TDH construction which satisfies both constraints. So let me give a brief discussion about the core idea. So let's start from the wild pairing on an elliptic curve. So that is a bilinear pairing, but unfortunately it is degenerate on any cyclic subgroup. However, there is a modification of the wild pairing by taking some non-scalar endomorphism and then putting the pairing EPQ as E hat PQ as EP psi Q. And this modified wild pairing will actually be non-degenerate on the cyclic subgroup generated by P. So this does actually help. So this does help solve DDH, but it's usually really hard to compute non-scalar endomorphisms on elliptic curves. So the main idea is to start from a curve which has a known endomorphism ring. So we started from J1728, a super singular elliptic curve, and then take some random walk in some isogeny graph long enough that the output, that it's hard to compute the endomorphism ring of the output curve. There are various technicalities on how to make this construction efficient. For that, please look at the long version of the talk or the paper. So what we've done, so we propose the new trapdoor DDH construction, which does solve Ceran's open problems. We also gave some partial attacks on Dent-Galbraith's construction when the group order is revealed. So it's a partial attack, so it only forces to increase the parameters slightly. And then we also gave some applications, so we managed to improve on an identification scheme proposed by Dent and Galbraith. And we also gave an applications to eVoting to say that to avoid super singular curves in that context. Okay, thank you.
Thank you very much. Please unshare your screen for the next speaker. Our next speaker is Simon Philip Mertz. He'll be presenting the paper on index calculus algorithms for subfield curves. I'm already seeing your screen, so you can go ahead. Thank you.
Thank you, Jean-François. This is joint work with Stephen Galbraith and Rob Granger and Christophe Petit on index calculus algorithms for subfield curves. The curves we looked at were Coblett's curves, so elliptic curves that are defined over a subfield compared to the extension field we consider the curve over. So if you think of the equation of an elliptic curve, it's basically one that has coefficients in some subfield, and we consider still all the solutions to the equation xy in the extension field. I'll use n as the degree in this talk. Half of the curves that have been standardized at some point by NIST were Coblett's curves over the binary field, like with two elements, but it's now highlighted that they are being deprecated. But they were popular for some time since they allow for faster scalar multiplication, which is because there is the Frobenius endomorphism, which is the map that sends one point to another point, raising the coordinates to the qth power. So this raises a natural question whether we can use this endomorphism also to speed up, well, variance to cryptanalyze the elliptic curve discrete logarithm problem. And the speed up for Pollard Row was actually presented at SAC20 years ago, SAC 1998. And Vina and Zuccaratu showed that the Pollard Row can be sped up for Coblett's curves by square root of this extension degree n. And our work was motivated by looking at index calculus methods and looking at whether we can speed up index calculus method on elliptic curves when Coblett's curves are being used. For higher genus curves, this problem was already considered in the past by Gaudry. So in index calculus, we pick a factor base. So it's just a subset of the group in which we want to solve the discrete logarithm problem. And then we solve the relation collection problem, which is just expressing some certain linear combinations of point as sums of factor-based elements, and then we keep collecting these relations until we have a matrix with as many linearly independent rows as there are elements in our factor base, and we're left with a linear algebra problem in order to solve finally the elliptic curve discrete logarithm problem. The relation collection step on elliptic curves is done by solving some huge polynomial system. And while previous work was dedicated at speeding up solving these elliptic curve, these polynomial systems, our work was focusing on how to choose a factor base such that we actually can maybe choose, need to find fewer relations. And the most successful variant was to basically choose a Frobenius invariant factor base. So that is one that is closed under the Frobenius endomorphism, because then if you find one relation, you can just throw the Frobenius endomorphism on it and you will basically get more relations for free. At least under the assumption that they are linearly independent. So one has to be careful a bit. But we can do even better. We can basically reduce this large factor base to one that is slightly smaller and just contains one element from each Frobenius orbit in our factor base. And then we can express that one relation in terms of the reduced factor base using that we know how the Frobenius endomorphism acts on the group that where the ECDLP lies in. And this results that we in the fact that we need to find n times fewer relations, and that also the matrix that we need to solve in the end in the linear algebra step is significantly smaller by n squared. One thing that I swept under the rug so far is that obviously we reduce the number of polynomial systems, but the question is whether they are equally hard to solve now with a new factor basis, and therefore we made some experiments, and the answer to that question is it seems to depend. So we gave multiple construction of such factor bases, and in one case it looked very well promising, and the other ones it didn't look very promising. I guess further work is needed here. Overall, further work is needed in evaluating how the structure that is introduced by picking these specific factor bases can be then exploited again in faster solutions of the polynomial systems, and also our experiments were rather restrictive on characteristics, and we couldn't solve very large instances, so further work is needed there as well. So to summarize our results, we show some instances where we can speed up index calculus by a factor of n in the relation collection and n squared for the linear algebra step. We give multiple constructions of Frobenius invariant factor bases. We also give a improved symmetry breaking for Koblitz curves. And overall, it should be like pointed out that while we managed to speed up index calculus up more on Koblitz curves than it was possible for polar rho still beats index calculus on Koblitz curves that are used in practice. So the security of these logarithmic improvements on the security parameters don't threaten Koblitz curves, and they remain strong. Thank you.
Thank you very much. Please unshare your screen for the next speaker. Our last speaker is Mattia Varoni, who will present the paper Practical Isogeny-Based Key Exchange with Optimal Tightness.
All right, can you hear me and can you see my screen?
Both, yes. Thank
All
you.
right. So yeah, this is a joint work with Bordecock and Christine Yerstin. In 5 minutes it's quite impossible to explain everything, but I will try to rush on every detail I can skip. So the importance of security proofs is well known. We like security proofs, and as many people do, because they allow us to assess the security of a protocol by taking an adversary against it and then turning it into a solver for a mathematical hard problem. And every time a scheme is implemented, one should choose theoretically some parameters for it. But different security proofs have different qualities. So
how do we measure the quality of a security proof? We look at the reduction, in which we turn the adversary into a mathematical hard problem solver. And we look how much we lose in terms of efficiency of the algorithm of the simulator. So this is the formula we use to define the tightness loss every time we build a reduction. So how much we lose in terms of efficiency when we design the mathematical hard problem solver starting from the adversary. And if we get a constant L, then we have a tight reduction. But in many cases, as in our simple reduction, we cannot get a constant L. And we can get something that's slightly worse, but still works very well. So in this case, we talk about optimal tightness because we cannot achieve the proper tightness, but we can prove that we cannot do better than that. So our research question was, can we get a tight quantum safe authenticated key exchange protocol? We couldn't, but we could do something slightly worse than that. So for those of you who are familiar to Seaside, these things are well known. So these are the parameters that are used in Seaside 512 for our protocol. So exactly the same. We have 74 small primes that are used to build this prime P, which is roughly 512 bits long. And then we start from an elliptic curve E0, which is fixed for everyone and is defined by the equation y squared is equal to x cubed plus x over fp. So we can arrange the set of super singular elliptic curves whose endomorphism ring is isomorphic to this order in a graph, and we can move along the graph using isogenies. So this is basically what we do. In order to generate keys for the protocol, we sample exponents, which are just integers, and are used to compute an invertible fractional ideal, A, as you can see in the second point of the key generation construction. And then we get the public key, which is simply an element of FP, by evaluating the action of this ideal over the initial elliptic curve E0. And we use this FP element as our public key. So it's really small. And the protocol that we obtain is taken from protocol Pi, which was introduced last year at Crypto. So we make use, as you see, both of long-term keys and ephemeral keys. And they are generated, as I just explained, and only two messages are exchanged. So we suppose that there exists a central authority which issues the long-term public keys. And in the real session that two users have to run in order to exchange a key, they only exchange two elements of FP, which are the Montgomery coefficients of the elliptic curve that results from the action of the ideal on the initial elliptic curve. But then we derive the final key by throwing in these many terms, which are not used only for crypto hygiene in order not for the users not to mess up with the sessions, but they are actually needed for the security proof because we can handle the adversarial queries with these terms. So we give the adversary quite a lot of power, and it can register new parties and it can activate oracles because each party in the protocol is represented through a set of oracles, one for each session it can participate in. And it can reveal long-term keys, it can reveal session keys, and in the end, it can test oracles. So this tested oracle will output either a real key or a random key according to an initial bit, which was tossed at the beginning of the simulation. And all oracles will issue random keys or real keys. So the adversary can break the protocol in three different ways. Breaking the key exchange and can guess, for example, the initial bits B. It can break the uniqueness of the relationship between partner oracles, or it can break the soundness of the scheme. So two partner oracles compute two different keys, but they accept it. So we built this very long security proof, which involves 6 different games, which is the actual selling point of the paper, and is not so trivial to adapt it from the original paper, because the protocol itself is trivially adaptable, but the security proof has some tricky parts. And by putting together all the games that we play in order to define the security proof, we get this tightness loss mu, which occurs 2 times here for these 2 adversaries. And this is actually the best result we can get if we use these simple reductions in which the adversary is run only once. So we don't run multiple copies of the adversary like with forking lemma. And as a quick comparison, we mainly compared our protocol with the protocol SAC, which was published last year at AsiaCrypt. And you can see we gain at least 1 order of magnitude compared to the efficiency of SAC, both protocols in that paper. And to summarize, so we have built this post-quantum key exchange authenticated protocol, implicitly authenticated, with optimal tightness. And we haven't compromised either the efficiency of the protocol or we haven't obtained huge key sizes. They are still reasonable. The adaptation was straightforward of the protocol itself. It was not that straightforward to adapt a security proof. And in the adaptation, for example, we need this random self-reducibility of CSAT problems and many other different small tricky parts. And for future work, we could prove our protocol secure in the random oracle model, but it can be maybe proved secure in the quantum random oracle model if one can collapse correctly the quantum queries from the adversary. So we believe that with the wise use of the quantum random oracle, you should be able to carry the proof on, but we're not sure of that. And it's also a problem if we have to handle with ephemeral key reveals, and how to move to this stronger security model in which we allow also that kind of queries is a bit tricky. And the last question is if we can adapt the protocol, but particularly the security proof in other post-quantum settings. So this is all. I think I went a bit over time, but thank you for listening.
Thank you very much. Now, we're going to take some questions. I saw a few in the Zulip channel. I'll start with what I have on paper 13. So these are questions for Sean Murphy, one from Ward. I'm going to read it out loud. Do you think the new algorithm would outperform existing attacks on the NIST PQC candidate GEMS? Looking at the NIST submission, it looks like they use a system of 164 quadratic equations in more than 164 variables.
Well, the short answer is I don't know. It's possibly. I mean, that's quite a big system, but potentially. We generally, for the method to work, we generally need 1 or just a few solutions. So 164 equations in 164 variables probably has only a few solutions, but we generally were looking at systems where we had more equations and variables, slightly more equations and variables at least. But I don't know until we try that question.
Okay, and on the same thread, there's a question from Jürgen Bulkus, who asked for about how many variables and equations would an implementation of your approach beat brute force for quadratic equations over F2?
Well, when we were constructing the paper, we were generally constructing it with a comparison against an Excel approach in mind. So we were coming up with places where we would think that we could do better than the Excel algorithm, which is in some sense the leading way of doing it. But we only ever put in a proof of concept to show that the method worked and worked reasonably well. For kind of detailed implementation questions like that, we would probably obviously have to do some much bigger experiments. So I think it would probably work better, but I don't know by how much. I mean, there are reasons for thinking it would work better, and we came up with an example in the paper where we had 63 equations in 20 variables, where our method only had to go to degree 3 cubic polynomials, and the Excel method had to go to degree 4 polynomials, which is a much bigger step. So there are certainly instances where it performs considerably better than Excel. But how widespread those instances are when you start getting very big numbers, I don't know. So that's a slightly incomplete answer.
Thank you. Thank you very much. I'm scanning through the Zulip channel and I'm not seeing any additional questions. So everybody, I remind you, if you want to ask a question, you go on the Zulip channel on the specific streams. Otherwise, maybe I have a quick question for Simon Philip. I felt like your method to increase the number of relations by acting with the Frobenius kind of reminded me of how when you use index calculus to calculate relations between, I mean, the ideal class group of a num field, and you act with the Galois group to see more relations coming out of the conjugate. Was that sort of a source of inspiration, or these sorts of methods?
I mean, I don't think it was that specific example, but the same idea has been also used for like just plain Galois fields, or like to increase index calculus, and by that one paper I mentioned by Gaudry for higher genus curves. I think maybe the contribution was less than that we used that same idea, but then that we constructed some factor bases that actually fit the idea and allow to gain the full speed up.
And then a follow-up question: when you mentioned the idea of also reducing the size of the factor base to have more manageable linear systems, is that something that stems out of the Q-descent idea of discrete log, and when you try to rewrite bigger primes as a product of smaller primes iteratively, or is it completely different?
I don't know. Like I think it's simpler in a way, because you can just reduce your like larger factor base in a ad hoc manner. It doesn't matter which representative you pick in the smaller orbit. You can just pick any, and then all you exploit is that Frobenius acts basically by a scalar multiplication on the ECDLP group, and then you just need to find the appropriate power of your basically the eigenvalue. But I'm not sure this answers your question.
I mean, it was a bit of an open-ended question, so of course it does. So thank you very much. I'm still scrolling through. We have a question from Alfred on Frost. So this is for Chelsea. Does the IETF community have some specific applications in mind for Frost?
Yeah, thank you for asking. I wanted to talk a little bit more about that, but it was a really short talk. So we've seen several use cases for threshold signatures, and there's kind of a desire to standardize threshold signatures, which is why NIST is taking steps toward doing that for threshold schemes in general, not just signatures. But there's kind of a lot of use cases around distributed signing. So for example, if you store secrets in like an HSM, you might want to partition your secrets among several HSMs. So that's like one use case of if you're doing signing like in a data center, or for some kind of like certificate management, for example. In a blockchain setting, it's desirable because you're signing actual transactions. We've seen examples, for example, in Tor, where there's a set of directory authorities and they assign a consensus for the whole network. So you also want to distribute trust in that kind of setting. So there's definitely a lot of kind of different use cases across domains, but primarily driven by wanting to reduce risk by partitioning secrets. among like several different authorities.
Thank you very much.
Mhm.
Well, do not see any further questions. If anybody has a last minute question, it's now or never. Going once, going twice. And well, I think this is the end of this session. So I thank again all the speakers from this session. I believe in about 10 minutes, there is a last word from the SAC program chairs at 12:30 Eastern time. Thank you very much.